Hello, discrete math fans. So this method that we just described for computing GCDs, it only works if we're able to factor the integers. Now, the fundamental theorem of arithmetic says that this is always possible. But it turns out that if we want to try to factor really big numbers, that can be computationally infeasible. In fact, this computational infeasibility is the mathematical basis behind crypto systems like RSA. Now, long time ago, thousands of years ago, Euclid came up with an algorithm that's a lot more efficient than just factoring the integers, or employing some trial and error method. Now first, let's state and prove a couple of lemmas. Now the first lemma is a technical point, and the second one is the entire mathematical underpinning behind what we're going to call the Euclidean algorithm. Alright, so our first lemma says that if r is a natural number, then the GCD of r and 0 is just r. Now remember, when we defined the GCD of two integers a and b, we said that a and b cannot both be 0, but it's okay for one of them to be 0. And that's what happens here. Alright, so to prove this, let's suppose that r is a natural number. Now we know that r divides r and r divides 0. So in fact, r is a common divisor of r and 0. However, there's no larger integer that can be a common divisor of r and 0, because anything bigger than r won't be a divisor of r. Therefore, the greatest common divisor of r and 0 is just r. Now our next lemma is the main lemma behind the Euclidean algorithm. And the proof of this lemma is going to show that two numbers, a and b, are equal to each other. But there's a trick with this. We don't have to prove that a is equal to b. What we can prove is that a is less than or equal to b, and then a is greater than or equal to b. If we're able to do that, then that proves that a is equal to b. Alright, here's our lemma. This is the main lemma. It says that if a and b are any integers, again, not both 0, and if q and r are any integers such that a is equal to b times q plus r, then we can say that the GCD of a and b is equal to the GCD of b and r. Now it's important to note that we're not necessarily using the quotient remainder theorem here. We're not saying that we have to divide. We're just saying if q and r are any integers such that this happens, then the GCD will stay the same. Alright, now let's outline our proof. It's going to go up into two parts. First, we're going to show that GCD of a and b is less than or equal to the GCD of b and r, and then we're going to show an inequality the other direction. Now once we've shown these two things, that's going to prove that these two GCDs are equal. Alright, so first part, we're going to prove that GCD of a and b is less than or equal to the GCD of b and r. And let's break this up into parts 1a and 1b. First thing is, we're going to show that any common divisor of a and b is a common divisor of b and r. Alright, so let's let a and b be integers. Again, not both 0. And let c be a common divisor of a and b. We're not saying that c is the greatest common divisor, just any common divisor. And what that means is that we're saying that c divides a and c divides b. Now, by the definition of divisibility, we can say that a is equal to c times n, and b is equal to c times m for some integers n and m. That's just from divisibility. Now, let's use our equation, a equals bq plus r. And what we're going to get is that first, nc, that's a, is equal to mc, that's b, times q plus r. Now let's solve for r. We're going to get r is equal to nc minus mcq, and if we factor out the c, we'll get that that's equal to n minus mq quantity times c. Now we know that n minus mq is an integer, so that tells us that c divides r. Now we already know that c divides b, that was one of our assumptions, so now we've proven that c is a common factor of b and r. Now we're not saying anything about greatest common divisors, just common divisors. Alright, now part 1b, now we're going to show that GCD of a and b is less than or equal to the GCD of b and r. So now we are going to talk about greatest common divisors. Now in part A, we showed that every common divisor of a and b is a common divisor of b and r. So this means that GCD of a and b itself, now we've proven that it's a common divisor of b and r, it cannot be any larger than the greatest common divisor of b and r, which is GCD of b and r. All right, that proves that the GCD of a and b is less than or equal to the GCD of b and r. So that concludes part 1. Now part 2 says that the GCD of b and r has to be less than or equal to the GCD of a and b. We flip the inequality around. All right, here's the deal. The proof of this is really similar. So what we're going to do is leave it as a homework assignment so that you get some practice writing these kinds of proofs. Now when you do rewrite this proof, it's going to look almost the exact same thing. Don't try to reinvent the wheel and get cute. Follow the same kind of outline. You should consider the Latin phrase mutatis mutandis. Maybe you've never heard this before. It means once the necessary changes have been made. So that's really what you're doing, is you're going to mimic the proof, make the necessary changes, and it's going to look almost the same. Okay, so this lemma is the main idea that's going to go into the Euclidean algorithm, that really we can reduce the calculation of a GCD into some smaller numbers, and we're going to see that with an example next. Okay, that's all for now.